So this is the first lesson of a new topic, kinematics, which is one of the three branches of mechanics. We've already looked at statics, that's the topic we've just done, and statics is concerned with Newton's first law. So this is situations where the resultant force is zero, the resultant moment is zero, and so there's no change in motion, either translational motion or rotational motion. Now we're going to be looking at situations where the motion does change. And that branch of mechanics has, well, two names. Kinematics is what we call it, when we don't care why the motion is changing, we're only interested in how it changes. And the topic after kinematics will be dynamics, which is interested in why the motion is changing. So looking at situations where the resultant force is not zero, or where the resultant moment is not zero. So let's focus on kinematics then. And there are quantities that we can measure in relation to motion. We can measure speed, we can measure velocity, as the title of this lesson suggests, speed and velocity. So what is speed? Well, speed can be defined as just the distance that something travels, distance a body travels, divided by how long it takes. Now, usually we refer to that as time. I prefer to call it duration of motion, because I prefer to reserve the word time for the temporal axis itself. But don't worry too much about that. So we've got speed equals some interval of distance divided by some interval of time. It can be defined as distance per unit time, where unit time just means 1 second if we're measuring in seconds, or 1 minute if we're measuring in minutes. Well, that's fine at GCSE level, but actually we do need to take speed a step further, because we could be talking about an average speed, or we could be talking about an instantaneous speed. So this is good enough for GCSE and not much more. So good enough for GCSE. So for A level, we do need to talk about average speed and instantaneous speed. So average speed, let's try and spell it right. Average speed is going to be the total displacement, total distance, goodness me, get that right. The total distance divided by the total duration. Now this is important because I've seen often at GCSE level, when asked to calculate an average speed, students calculating maybe 3 different speeds, adding them together and divided by 3 and thinking that's okay. That's not what we mean by average speed in kinematics. In kinematics, what we mean by average speed is just this: the total distance divided by the total duration of motion, or call it time if you like. So speed equals distance over time, distance is speed times time. All of that is still true, there's nothing wrong with it, it's just a bit basic. Are we talking about an average speed over that particular distance during that particular duration, or are we talking about an instantaneous speed? So we'll come on to instantaneous speed a little bit later. I'm not sure if it's going to be this lesson or a later lesson, but we will come on to instantaneous speed. In fact, let's just do it now. We might as well do it now. So let us suppose that we have a graph. Let's make it quite small so we can fit everything on. A bit not quite that small, so that we can fit everything on the graph. And it's only going to be a quick sketch. On the y-axis, we will have our distance in whatever units we're measuring our distance in. Maybe centimeters, maybe meters. And on the x-axis, we'll call this time. So maybe we shouldn't call this distance. Maybe we should call that some sort of spatial coordinate. in the same way as this is a temporal coordinate, but we could get ourselves in knots with that. So let's say we've got motion like this. If we want to know the average speed up to this particular time, let's do that as a solid line rather than a dotted line. If we want to know the average, then it would be the total distance divided by the total time. So it's going to be this quantity divided by that quantity. We can call this one S, we can call this one T, and so we can say that the average speed is equal to S divided by T. But if we're interested in the instantaneous speed, so perhaps we're after the speed at this particular time there, well, then we're going to have to draw a tangent. We did this in GCSE level. None of this should be particularly new. You're going to have to draw a tangent, probably a better tangent than I've just drawn, but I do have the advantage of being able to move it. That'll do. And the gradient of that tangent is going to be the instantaneous speed. And I'm just going to call that V. And that's going to be the ds divided by dt. Now that may be new notation to you. So let me just write down that this is the gradient of tangent, and that is also equal to the instantaneous speed at that particular instant in time. That's labeled with that green line. Okay, fine. And that is pretty much as far as we would need to go with the difference between average speed and instantaneous speed. So this notation, this d by dt, meaning a gradient, if you're really interested in that, I do have a video series of about 12 videos, I think it is, called Physics, well, what's it called? Calculus for Physicists, or Calculus for Physics Students, or something like that. And in that video series, I work through the principles of calculus from first principles all the way through to every bit of calculus that's useful for A-level physicists to know. So if you're studying A-level mathematics, then you'll cover all of these things in A-level mathematics. Not everyone who does physics studies A-level mathematics, and yet it's still useful to know calculus anyway, for some of the derivations in particular. And we will use calculus on the A-level course, so there's no harm in learning about it. If you've done GCSE further mathematics, you may well have learnt about differentiation, but not integration, and all of that is part of this topic called calculus. I remember when I was much younger, I just thought calculus meant using a calculator. No, it's not that at all. It's the mathematics of very small changes. So that's what we mean by d by dt in this particular expression that I've written in green. We could use capital delta, the Greek letter delta, to mean a change in, which is what appears more commonly when we look at tangents, for example. With calculating the gradient of a tangent, it's a discrete change along the y-axis and a discrete change along the x-axis. It's something that we can actually measure off the axes. The whole point is that the curve itself, well, that doesn't have a there's no straight part there where we can just calculate an interval across the x-axis and an interval across the y-axis. We can't do that because it's a curve, so that interval would be changing relative to the other coordinate all the time. So we could say, and then I will write this down here, that gradient of straight line, like the tangent, you could say that is equal to delta S divided by delta T, where the deltas mean a discrete change, but gradient of a curve or a curved line, we would have to talk about ds by dt here. But ds by dt could also be used for a straight line. Okay, we haven't got very far yet, have we? So what about if we've got constant speed? Well, if we've got constant speed, then the line on this graph will be straight. So I'll say for constant speed, distance versus time graph is straight. Graph straight line. That's what we'd expect to see. And we can get that in a couple of ways. I mean, one way we can get a constant speed is by having something just moving in a straight line and having no resultant force on it. However, we could have a situation where we've got a constant speed and there is actually a resultant force acting on it. Now, that seems odd. And if you remember from GCSE, if we've got a resultant force acting on a body, then there will be an acceleration of that body. So how can we have an acceleration but also have a constant speed? That's because acceleration is defined as the rate of change of velocity, not the rate of change of speed. And we'll be moving on to acceleration next lesson. But what I will say is we can get constant speed if we're moving in a circle. If we're moving in a circle, we have a resultant force towards the center of the circle. That's all part of the A level that comes up later. But that is an example of constant speed as well anyway. So we could say for movement in a circle, or for motion in a circle of constant speed, how do we calculate what that speed is? Well, it's the same thing. We could say that the speed, so that's v, which would be the average speed or the instantaneous speed, because if we've got constant speed, the average speed will be the instantaneous speed by definition. That's going to be equal to the total distance we travel divided by the total time. Well, let's suppose that we make one full circle. We can call that t, the time period, the time it takes to go once around our circle. And the distance we've traveled is the circumference of that circle, which is 2 pi r, or pi d, where d would be the diameter. And you remember from our wave equations that we've already studied, if you're watching these in the order that they're recorded, it might be doing it in a different order, in which case, well, include this in your notes, but it's going to be useful for a later time, that 1 over t is equal to f, the frequency, and we end up with that equation there. So that's constant motion in a circle. And that is the instantaneous speed, but also it is the average speed, because they're the same thing if we've got constant speed. Maybe I should make a note of that as well. Maybe that's too obvious. So for constant speed, we could say instantaneous speed, that's the speed at a particular instant, is equal to average speed. Just useful bit of information to know. Okay, so we've talked a little bit about distance time graphs with our little sketch there. Distance traveled divided by the time taken is the gradient of the line. It's all there in our notes. So let's move on to velocity then. This is all about speed so far. So what about velocity? And in GCSE level, you learn that velocity is just speed in a particular direction. And that's true, but we're going to define velocity in a slightly different way. We're going to say velocity v, and because it's a vector, I'm going to do that notation of drawing an arrow over the top, is equal to, it's not distance anymore, because this must also be a vector with an arrow over the top, divided by our duration of motion. Or we could say that this thing called s with an arrow over the top is equal to this thing called v with an arrow over the top multiplied by the duration of motion. Now that is the average velocity. average velocity, not the instantaneous velocity. So what is this average velocity? Well, it's the rate of change, but what is this average velocity? Is just the change in displacement divided by the duration. So s is not distance now, it's displacement. We use the same letter, s, which comes from the Latin spatium. So s is the there's not a lot of space there. Let's draw it over here on the right, so I've got a little bit more space. It's pun not intended. S is equal to displacement. Now, in printed text, vectors will usually be written in bold. But I'm handwriting this, so I'm indicating vectors with a line over the top. So displacement, yes, it's distance in a particular direction. Yes, I'm sure. But displacement can increase or it can decrease, whereas distance can never decrease. You can never undo the space through which you have moved. That's one way of thinking about it, is distance is the space through which a body moves, and that can never be reduced. Whereas displacement is the straight line between the start point of the motion and the end point of the motion. And that line has a direction. So when we talk about velocity, it's a vector and it's in the same direction as the displacement. Let's just show you this equation. These are the two vectors in that equation. There's an equal sign between those two vectors. And those are the only two vectors, which means that the direction that's contained in the variable s has to be the same as the direction that's contained in the variable v. It must be. That's how the equal sign works. So on displacement time graphs, unlike distance time graphs, on displacement time graphs, we can have a reduction in displacement. In fact, I'm going to write this down. Distance cannot reduce distance is space through which, you won't find this definition anywhere else, a body moves. Now, colloquially, we'll just say distance is how far away something is. You know, what's the distance from me to my shed? And I could measure that in meters. And I can make that distance smaller by moving towards the shed or bigger by moving away from the shed. In physics, we wouldn't call that a distance. Distance is the space through which a body is moved. Whereas displacement can reduce. If you ever see a distance time graph and the line representing the motion of a body is going down, the distance is reducing, then it's incorrect. It's simple as that. So displacement can reduce. It is the, let's say the shortest rather than the straight line. Euclid described it as a straight line. The shortest line, and remember lines can be curved, connecting the start of, that should be start of the motion of a body to the end of that motion. Okay, that's what it is. So if I had a displacement time graph, it might look something like this. And I'm going to label these displacement and this one time. Maybe we've got a graph that the data does something like that. I don't know. Then we could say that the gradient, we could say the velocity is equal to the gradient of this line. So that is going to be d by dt, that's the gradient of that. So ds by dt, that's how I would like to write it. And because it's constantly changing, we can't use deltas, but we can draw tangents to calculate this. So graphically, we might draw a tangent. So graphical determination of this quantity by drawing a tangent. Spell tangent, right? And then computing the gradient of that tangent. And that's what velocity is, the rate of change of displacement. It has a direction. So if we have simple one-dimensional motion in this part of the graph over here, we are increasing our displacement, so we could say we're moving forwards. But in this part here, we're decreasing our displacement, so we could say we're moving backwards. So the gradient also has a direction. And the direction of the rate of change of that displacement is going to be the direction of the velocity. And I think that's all I really need to talk about in relation to velocity and speed. We've talked about how distance differs from displacement. We've talked about instantaneous speed and average speed. And we know we need to consider velocity when we're interested in direction, when direction matters. Okay, I will stop there. And I hope that's been useful. And I hope you consider joining me in the next video.